Welcome, everybody, to the first inaugural science interview on the new YouTube channel. As with the live events, there will probably be some kinks that need to get worked out. But I really appreciate the folks I have today being the first guests on the new Weather West channel. And I think we'll maybe go around and introduce ourselves, perhaps in authorship order of the paper that sparked this conversation. So maybe we will start with Sam.
Yeah, hey, I'm Sam. I'm a third year PhD student at Columbia at the Lamont Doherty Earth Observatory, so the work we're discussing is part of my PhD work, and in general, what I've been working on is extreme heat and the mechanisms of extreme heat worldwide, and with some intersection with a little bit of atmospheric chemistry and near surface air quality.
Excellent. Kai?
Yeah, thanks for this invitation. I'm Kai Kornhuber, adjunct assistant research scientist at the Lamont Doherty Earth Observatory, also a lecturer at the Columbia Climate School, and senior research fellow at the German Council on Foreign Relations. And overall, I'm working on physical climate risks, more specifically on atmosphere dynamics, and also climate impacts such as multiple breadbasket failures due to concurrent heat extremes and other compound extremes.
Great. Thank you, Kai. And Mingfang.
Hi, everyone. My name is Mingfang Ting, and I'm a Lamont research professor at the Lamont Doherty Earth Observatory of Columbia University. And I'm also co-senior director for education at the Columbia Climate School, which is a very new school that was founded a couple years ago here at the Columbia. And I also co-direct a master's program in climate society, which emphasizes interdisciplinary education for master's level students. My research is focusing on mostly climate variability, climate change across a wide spectrum of topics. And to be relevant here, one focus of my research is on climate extremes, including droughts, floods, as well as heat waves, as we will be talking about today.
Excellent. Thank you. I'm, genuinely impressed you managed to get everybody in the same virtual room all at once on a weekday. So I greatly appreciate that. That's not easy to do with the full deck of authors on any scientific paper these days. So thanks again for joining me. And I'm excited about this because not only was I impressed by this paper in particular, but I really thought it is a nice segue into some broader questions about climate change and extreme events and how we know what we know about extreme events in a warming world and how we know what we don't know about those things as well. And that's actually something that you directly allude to in the paper. So just to introduce everybody, what we're talking about today, or the conversation, is inspired by a paper focused on the exceptional heat wave that occurred in the Pacific Northwest in the summer of 2021. The paper was published in Nature Climate Change recently, just this past November 2022, and is entitled 2021 North American Heat Wave Amplified by Climate Change-Driven Nonlinear Interactions. And you have all the authors on your screen right now. And, this topic is an important one, of course, because the heat wave in its own right had tremendous impacts in the Pacific Northwest. It was essentially the deadliest weather event in Canadian history. We don't often think about heat waves as causing a real threat to human life. We're more familiar with the perhaps more visually dramatic kinds of natural events, extreme storms, tornadoes, floods, hurricanes, things or wildfires in terms of climate-related things that might be life-threatening. But in a lot of cases, it's really the heat waves that cause the most morbidity and mortality. And that was certainly the case here. there were also extreme consequences for ecosystems in the region, both marine ecosystems, terrestrial ones, and freshwater aquatic ones as well. And then these events were followed by major wildfires, especially across the interior and in British Columbia. So this was an event that spanned two countries, the northwestern United States and southwestern Canada, and really just brought temperatures that weren't just record-breaking, but they were truly record-shattering. They were temperatures so far beyond what we had seen historically at any time of year in a lot of these locations that it shocked even seasoned meteorologists and climate scientists. This was a genuinely out of left field event. And so the paper, I think, is just for that reason alone would have been well motivated. But beyond that, there are questions then. If we know that we can see events of this extreme record-shattering magnitude here, why not elsewhere? And what are the implications more broadly for extreme heat events, certainly, but also extreme events and how we quantify them and how we ask questions about them in a warming climate where conditions are very different. In some cases, non-linearly so, as we'll talk about today. So that's probably enough of me talking for now. But what I did want to sort of start out with is just a brief overview of what you found about this heat wave and its links to climate change. Anybody who would like to go can go, but perhaps we should start with Sam, since he is the lead author.
Yeah, so that was a great overview of sort of the multi-systemic impacts of the event that really were sort of what motivated our study, because we wanted to take a close look at what the physical causes of the event were on a couple different scales. So of the time scale of the event itself and how it happened, but also linking back to longer term things like climate change. And yeah, we wanted to sort of dig down into the physical mechanisms of the event, and what we ended up finding was sort of on the most basic level was that the event was caused by a multitude of factors in a multitude of different systems or subsystems of the Earth system, and so there's a clear contribution from things like the dynamics of the atmosphere, but also things like the dynamics of the land surface and how that interacts with the atmosphere. And sort of the main takeaway is that there were a combination of factors that ended up causing this very extreme event. And some of those factors were likely strongly related to climate change.
And so, what I thought was interesting is that you find that, unsurprisingly, there was a very strong high pressure ridge, essentially, co-located generally over the Pacific Northwest. So, we often see strong high pressure and ridging in the warm season when there are heat waves. That is sort of the nature of things, because that's the kind of circulation pattern that tends to suppress clouds and precipitation on the one hand, and also bring warming through the downward motion of the air in the atmosphere itself through subsidence. But of course, in this case, that's not the only thing that was happening. As you alluded to, there were also connections to the land surface and soil moisture feedbacks. And what was the relative balance between those two things? So to what extent did you find that the unusually intense high pressure system produced these extreme temperatures, and then to what extent were these other nonlinear factors like these soil moisture feedbacks, which of course can eventually form a vicious cycle during the heat wave itself, as the heat continually dries out the land progressively more the longer the heat wave goes on, the stronger that feedback, that vicious cycle can become as the air heats the land, dries out the land, which then begins to heat the atmosphere because there's less energy going into evaporating the water that's no longer there. So do you have a sense of what the relative importance of those factors were in this particular case?
I think that the atmospheric dynamics were definitely the primary factor. I mean, the way the atmosphere was arranged exhibited sort of such a strong forcing that can explain most of the heat that was eventually observed at the surface. The ridge was the anticyclonic circulation that created this ridge was so strong that the temperatures that would have been forced by just that alone would be very high and likely record-breaking. And the relative balance then is such that it's likely that in some areas of the Pacific Northwest, the dry soil then further amplified that heating. And that's sort of, I think, how we see the balance, is that there's this strong forcing from the atmosphere itself, and then in some places that was further amplified by the land surface processes.
Right.
I think the two are not always completely separable, the atmosphere dynamics and the land atmosphere interaction, because when you have anticyclone, then you also dries the region and the land. So that then feeds back. So that's why we call it nonlinear feedback. So that nonlinear feedback, I think from statistical estimate, we estimate it to be like maybe 30% amplified. Because of that, Sam, please correct me if I was not accurate on that. But I think in this case, it's more of the sort of the background warming. So, you always have this land atmosphere interaction happening, co-occurring with the anticyclone when you have a heat wave event. But in this case, I think this is amplified also by the fact that there's a general warming, a drying trend in this region. They used to be very moist in the area, and now there's a clear trend going toward getting drier. So in that sense, whenever you have a dynamics atmospheric condition that's ready and kicks into this land atmosphere feedback, that can be much stronger than if the land were, still moist, considered a wet region. So that I think accounts quite a bit of this, why this event is so exceptional.
And you bring up an important point here about the fact that in this region at this time of year, the background conditions have been drying, which I mentioned because the Pacific Northwest has not actually been drying the rest of the year. So this is an interesting case where the season in which it's most relevant for heat waves, it's doing the atmosphere essentially and the land surface are doing something different than they are, say, in winter or even in autumn. Or in many places, we're seeing more precipitation with climate change. That's not true in the summer. And so that really points to the importance of being seasonally focused in these analyses. This is something we sometimes run into where people look at annual trends, which can really mask important processes and feedbacks that exist at regional and seasonal scales. I think this is a really classic example of something that you probably wouldn't have seen if you had just looked at annual trends. But because you're looking specifically at this early to midsummer period where there are some very strong trends that are different than the rest of the year, this really pops out of the woodwork as a much more significant factor, perhaps, than it might have been in a different season or a different place.
Absolutely. I think that also applies to your question earlier about other regions, right? In other regions of the world. I think that certainly what we find here can apply to regions where you do see in certain part of the year that there is this drying trend. And if that exists already, and on top of some kind of atmospheric driving condition, perfect condition for a heat wave events, that can make the events much stronger.
Yeah, another area that comes to mind would be Western Europe, and in particular the Mediterranean region, where we have seen really extraordinary heat waves also past year, where, we just had another example of record-shattering heat wave with temperatures hitting around 50 degrees or so in Spain for a couple of days in midsummer. And it's also, in winter as well, but in summer the heat wave was particularly strong.
And that was true. I mean, the Mediterranean, of course, it was hottest in that extraordinary heat event this past summer, in summer 2022. But Northwestern Europe was no slouch either, getting above 40 centigrade in London. You know, seeing those images of vegetation fires that looked like something a scene out of California within the city of London last summer was pretty stark. And that sort of alludes to this idea that, you know, that you directly mentioned in the paper, that some of these soil moisture feedbacks where drying of the land surface can non-linearly amplify heat waves is probably most pronounced in places that are these transition zones where it's neither very wet nor very dry to begin with. Because if it's very wet to begin with, you have to dry things out a lot for these feedbacks to really come into play. And if it's already very dry, then there really isn't any additional water you can lose from the system to amplify the heat waves. But anywhere in between, where you sort of have conditions that are somewhat wet, you have a lot of room for further warming and drying to really amplify heat waves. And so these are sort of the hot spot regions, these transition zones between wet and dry conditions where you might expect these feedbacks to be strongest. But of course, that's not a static thing. So in the paper, you mainly talk about it in terms of regions, but this really made me think about seasons as well. You know, like a place like California, for example, or the United Kingdom, for example. California is very wet much of the year, but then very dry the other half of the year under typical conditions. And so you probably have a transition season where perhaps you might see strong amplification of heat waves, and then a season where it would be less important. At times of year where it's already extremely dry in California, this effect is probably lower. But maybe in these transition seasons, in the spring and autumn, and in autumn where we've seen incredible heat warming in California, for example, perhaps this is important. In the UK, for example, a place that's normally quite wet, but was not this past summer, which really enabled, I think, these sorts of processes to unfold. So the fact that these things are not fixed in space or time necessarily, and can be conditional, you know, transition regions certainly, but also transition seasons, and perhaps even sort of extraordinary preconditions. So the UK is likely not to become dramatically drier in a warming climate. In fact, perhaps the opposite on average. But conditionally, during a severe drought, that really set the stage for that heat wave to go haywire. So I think there's some interesting parallels, you know, around the world. Also, the events that we saw in China this past summer. This past summer was another really extraordinary summer of just wild heat events in many places. So I was really intrigued by that.
Another area that would come to mind is probably Siberia, or the high north in Russia, where you have these very complex cascades of early snow melt, which then leads to an early greening of the biosphere, but on the other hand, also a lack of water later in spring, where it would usually be required to keep the soil moist. And this, to some degree, led to this extraordinary heat wave in 2020 that we saw back then. So these more complex interactions between different parts of the Earth system also become more and more important in driving extremes as the globe is warming and is affecting more aspects. And maybe to segue into another very interesting aspect of this study, or the overall question, is probably one aspect that climate models are struggling to reproduce to some degree, because the snow dynamics are really complicated, as are soil moisture aspects to model. And this heat wave shows that these aspects are just very relevant for driving these extraordinary extreme events. So this might be one factor that limits the representation of such extraordinary extremes in climate models.
And this is a good segue into something else I was hoping to talk about, just as a reminder to everybody who's listening, that climate models are essentially these mathematical representations of the physics and thermodynamics of the atmosphere, but increasingly it's not just the atmosphere. Increasingly, these mathematical models are coupled to other components of the Earth system. So the land surface, the soil, the biosphere, so the plants that exist on the land surface, the oceans, of course, that's a big one, and also the cryosphere, sort of the frozen part of the world, the ice sheets and the sea ice, things like that, and land snow cover as well. And all of those components turn out to be really important. Pretty much anybody who does a study where you perturb any of those Earth system components anywhere on Earth, it affects a lot of places on Earth. So the more we do these experiments, the more we find that as Mingfang mentioned, that these things are sometimes difficult to disentangle because it actually looks like everything matters all the time. It's just a question of to what degree and in what way. And those are questions then that matter whether or not you have the processes right in your models. And we know that in some cases, the land surface models, the cryosphere models, they aren't as advanced in terms of the representation of the underlying processes in physics as are the atmospheric components of these models. We have quite good weather models, for your daily weather forecast, and a lot of the same physics is in climate models. It's a different time scale. But at a fundamental level, we understand atmospheric physics pretty well, or at least better compared to the degree to which we understand the processes and the coupling between the land surface and the atmosphere, and the ocean and the atmosphere. None of them are perfect, but I'd say that the atmospheric component of the models is the strongest part at this point. Perhaps others might disagree with that, but that's sort of my view on this at the moment. But that these other pieces of the puzzle are, the more we look at them, the more we realize they're really important. And so I think that's a good segue into sort of talking about, well, how we know what we know about these relationships. And so first of all, I guess this is a two-parter. One is, since I guess we haven't touched on it yet, quantitatively, what did you find to be the influence of climate change on this particular record-shattering heat wave in the Pacific Northwest? That's, I guess, part A. And part B is there have been other studies that have looked at this heat wave and found they all find that climate change significantly increased the likelihood of what was observed. So that part, there's essentially unanimity, which is not surprising because that's generally the case for any extreme event attribution study we do on heat waves these days. There's essentially always a human fingerprint. You can almost say that without doing the study. The question is how much. And in your study, you find a much larger fingerprint, essentially, of human-caused climate change than some of these other studies. But on the other hand, a lot of these other studies haven't closely considered the potential that there were nonlinear feedbacks, which you find to be responsible for, I believe it's about 30% of the magnitude of the event. So that's quite a considerable increment beyond what you would have just gotten from the long-term mean warming trend. So first of all, what is that factor overall that you find, and how important is it that you are able to include nonlinear factors, which you do really in two ways. One, by using statistical approaches to sort of tease out what that fractional contribution is based on observations, and then also using a process-based modeling approach to sort of say, okay, does this comport with our understanding of how the physics should be behaving in the system? So it's really like two or three questions I threw at you, so feel free to go at them in any order you want, and anybody can join in.
Yeah, so there's definitely a lot of components to that. One thing is sort of how did we determine this fractional component of the sort of nonlinear amplification of the events. And that is nonlinearity that some of it will likely have to do with these land atmosphere feedbacks, some may not. And we didn't specifically tease out how much of that impact was versus was not. But that is just sort of a estimate of how much the eventual temperatures that were reached were sort of more than the sum of their parts in terms of decomposing the impact of sort of the atmospheric dynamical forcing versus the soil moisture anomalies that were present at the time. And the one thing we saw was that looking historically, so yeah, just based on this historical analysis, is that the processes that likely influence that nonlinear component are associated with these historical trends, where they may be increasingly likely to influence heat extremes. And segueing into at that point we wanted to segue more sort of into the model world to see if we could get a closer understanding of those sort of effects. And that's where we started to look at sort of this one climate model experiment where we, as you mentioned, in a climate model, you can perturb different parts of the model. So we looked at this climate model where it was run a bunch of times over a historical period. And by run, I mean there were historical sea surface temperatures forced into the model, and then the atmosphere sort of evolves in response to that. And that proceeds over the course of 100 or 140 years in our case. And so this model was run a couple of different ways. Manually, one way it was run was all of the parts of the model were interacting with each other. The second way it was run was where the soil moisture in the model was not allowed to interact with other parts of the model. So the soil moisture was sort of relegated to acting by itself and not sort of influencing the atmosphere. So the atmosphere wasn't listening to the soil moisture at all. And these sort of feedbacks would then not be allowed to develop. And so
essentially you created a counterfactual world, if you will, where the soil moisture cannot interact with the atmosphere, and compared it to the one that more closely approximates the real world, where we know that the land surface does interact with the atmosphere, to look at what the difference is.
Yeah, exactly. And so the question that is targeted at is, typically in the Pacific Northwest, what can the role of the land surface be in influencing heat extremes? So without even regard to this extreme event that we did see, what is the plausible effect of the land surface on influencing heat extremes in that area? And so, as you mentioned, it's like these transitional zones that typically these feedbacks are potentially important. And one thing that's important is that within the Pacific Northwest, there are a variety of different ecosystems. So by the coast, it is super wet, and there are these rainforests that are allowed to be there because there's so much precipitation. And so the soil is basically always wet. There are some places also within the Pacific Northwest where it's super dry. And in both of those extremes, it's likely that there isn't this possibility for the soil moisture variability to have much of an effect on temperature. But then also within the Pacific Northwest, there are regions that are this more transitional zone. And so when we were doing this model experiment, the takeaway was that on average, sort of the aggregate effect over the whole Pacific Northwest, so taking into account all these regions, the effect is that typically the land surface can have an influence on extreme heat events. So what we looked at in these two different configurations of the model was that in the sort of real world one, so without soil moisture artificially limited, in the real world imitation, extreme heat events were more likely to happen or likely to be more extreme than they were in the counterfactual model, where soil moisture was artificially limited from interacting with the atmosphere.
Maybe to add what Sam just said, the attribution aspect, which is based on the generalized extreme value distribution fit, does actually yield very similar numbers to what other studies have shown, at least are in the same ballpark. And given the large uncertainties when estimating those numbers, I would say that they are somewhat yield the same message, which is, as you already said, always, anthropogenic greenhouse gas emissions have substantially increased the chance for such an event to occur, and will also make it more likely as long as these emissions continue, and even more so if they continue to rise, as we're currently seeing, unfortunately. So the results are that the event probability, which is currently estimated as a 1 in a 200-year event, will increase to a 1 in 10-year event in a 2-degree world, which is more or less what Philippe et al., the authors of that rapid attribution study that came out a couple of weeks after the event found as well. I believe they are stating a return time of 5 to 10 year event in a 2-degree world or so, which I would say is really the same result. But it also shows that it is extremely difficult.
Is that for the specific region, or is that sort of anywhere over the northern hemisphere? I'm not sure I'm recalling exactly what that statistic was.
I believe they just focused on that region, but their exact metric might be a bit different. That is true. I'm not sure if they looked at daily maximum temperatures. I think we might have focused on daily anomalies or so, right? So there are these small differences that might alter the result. Like, really depends on what you define as your event.
Just to interject there briefly, just to really drive home the point of what you just said with some of those numbers, that the specifically, and this is, as you mentioned, relatively consistent with some other studies suggesting a strong influence of climate change on this event. What you specifically found was that the heat event that occurred in the summer of 2021 in the Pacific Northwest was essentially impossible to have occurred even just in the 20th century climate with a little bit of global warming. It was functionally impossible at that level of warming. And even today, it was an extraordinarily exceptional event. Even in the present climate, I think you just mentioned something like a 1 in 200 year kind of thing. So something that would have a 0.5% of a chance of occurring in any given year at this point in terms of how much we've already warmed. But that by the time we get to 2 degrees centigrade of warming, and not only are we already more than halfway there, but we are currently still on track to significantly exceed 2 degrees centigrade of warming, even with some of the more optimistic climate trajectories that have been set forth in recent international agreements. So this is something that we are very plausibly will get to within many of our lifetimes. That the likelihood of an event like what was considered to be just this earth-shattering, implausibly, almost unbelievably extreme event just last year would occur on average every 10 years at that point that we could get to just a few decades from now. That's an incredible statement about how much climate change is influencing the likelihood of things that were just literally unthinkable as recently as a couple of decades ago.
Certainly the bottom line takeaway is that something like this would really have been virtually impossible in historical conditions, even going up to pretty near to the present. So as you mentioned, throughout sort of the 20th century, and even towards the end of the 20th century, where we even had a little bit of global warming baked in, something like this would still have been considered virtually impossible. So something like potentially many thousands of year event or something like that. But even at the level of global warming we're at now, which is maybe 1.2 degrees Celsius globally or something like that, the current level of warming has transformed it from, even with that about 1 degree Celsius, has transformed it from something that's virtually impossible to something that's maybe estimated to occur every multiple hundreds of years or something like that. So that shift is in probability, that multiplication in probability is extremely strong, just from this sort of steady rise in global temperatures. And then as we increase that warming, the probability goes up extremely fast. And so in the future, it could be something like a decadal event or something that happens with like a 10% probability every year if we reach global warming levels of something like 2 degrees. And of course, there's huge sort of uncertainty in those numbers because these probabilities are fundamentally still very low. I mean, if you think about the probability of this event, it's still an extremely rare event. And so there's a lot of uncertainty associated with these numbers. But the takeaway is that there's this very robust upward shift in probability for these really extreme events. And that's something that's generalizable to not just this region, but pretty much every region globally.
The reason for this uncertainty, of course, is that these events are so rare, right? So it's so difficult to model them statistically, but also, as we show in this paper, we know these different factors that contributed to that particular event all have their climate change-driven trends as well. And if this hypothesis that we state here is true, these numbers might still be conservative estimates as they are to some degree ignorant of those nonlinear effects that might kick in at a specific warming level, which just have not occurred as often in the past. So this is something I think we should be even more worried about, because these recent clusters of extraordinary extremes that all have been to some degrees shocking at the time they occurred. We just tend to get used to them. Does suggest that there are some trends that are not really anticipated by climate models as to date.
And that's a good segue, I think, into one of the other more, broader philosophical things that I sort of wanted to close with, which is a question that I think all of you might be able to reflect on about unprecedented and record-shattering events generally in a warming climate, certainly as they relate to extreme heat, because we've seen a lot of them. We're starting to understand the processes and understanding what we don't know about the processes that are relevant and how we may be underestimating some of them in certain regions. But also just more broadly about thinking about, and I think you even use this language in the paper itself, about whether this was truly a quote unquote black swan event, something that was totally unforeseeable from what we already knew, or whether it's really not quite that kind of event. It's more like what is now colloquially referred to as a gray swan. So still an event that is extraordinarily disruptive and that we didn't necessarily see coming, but that we could have seen coming if we had thought about in a circumspect way some of the various factors that were involved, where there are traceable pathways. It didn't truly come completely out of left field, even though we didn't happen to see it coming. Perhaps we could have, and perhaps we now can use that knowledge and extrapolate it to other similar kinds of events. This kind of terminology has been used in the climate space before. There was a paper by Carrie Emanuel a few years ago about tropical cyclones in a warming world, and how certain kinds of events, certain very intense tropical cyclones in certain regions that haven't even seen tropical cyclones before, are possible if you have a long enough view and you have enough climate change. Things that you once thought were impossible, high-end tropical cyclone near Dubai. We've certainly never seen one of those before, but there is an awful lot of warm water nearby. You just don't typically have the conditions necessary to produce a storm in the first place. But if some exceptional confluence of conditions were to occur there, with another degree or two of global warming, you could see that. And this is sort of generally true. The analogy, heat waves are maybe less of an exotic phenomenon because most people on Earth have experienced them to some degree, in their lifetimes repeatedly. But in a lot of ways, because they're so common, it's actually a much bigger problem because everybody is going to be experiencing this increase in heat waves. And if we've underestimated the gray swan events, even if they're not really black swan events, even if they are somewhat foreseeable from what we already know, they're still wildly disruptive. And so what does this tell us about sort of understanding extremes in a warming climate and trying to ascertain where the weak points in our understanding of the underlying processes actually are? I'm just curious to hear thoughts from folks who I think have done a really a thoughtful analysis in this paper of how to address it in a pretty specific context for specific kinds of nonlinear interactions that we know should exist. How can we do this systematically? And what does this tell us about sort of where we are in the science and in the real world in terms of adapting to or dealing with these kinds of things?
I think that's a very good question. Obviously, something we've thought a lot about. I want to bring back something Kai mentioned earlier. Is climate model underestimating this kind of extreme event that we experience in real world? I think the answer is probably yes. I think we do have a lot of climate model runs, like what we call large ensemble. So you run the historical emission for the coupled ocean atmosphere, land surface, the Earth system model basically for centuries at a time, and many, many realizations of that. And you could estimate what is the likelihood of this kind of event happening in the world, in the model world. In fact, I think there was a paper out talking about that. And my recollection of that is that this, even taking into account the climate change signal in the model world, this event is very, very rare, 1 in 10,000 years. So that tells us, our models are probably underestimating this kind of event. So we do need to look into why the models are underestimating. And one of the factors that can be misrepresented in the model is probably how important the land-atmosphere interaction is, the nonlinear amplification, how well the models are representing that kind of process, and how much that contributes to the underestimation. And as you pointed out, many of you said 2022 is another year. It's not only one region, but across the world in the Northern Hemisphere summer. We see these kind of events, all of us are like completely shocked to see these happening at this time scale, like right now. We expect these to happen in the future, but it's happening now tells us that our understanding is not quite catching up with the real world.
Yeah, I think you were referring to that really nice analysis by Karen McKinnon and Isla Simpson there, Mingfang, which I find really, really helpful as well to understand, first of all, what types of regions are particularly susceptible for these very strong temperature anomalies. They refer to this, to this particular characteristics of the distribution of the temperatures there, which do feature a very large skewness. So they actually show that this area has experienced very strong temperature anomalies in the past. So to answer your initial question, was this to be expected? Possibly yes, if we would have paid a bit more attention to what happened in the past and what a bit of additional warming does to the statistics. And also, what I find very interesting is that they show that models are able to reproduce such extremes under specific conditions, but that they just do it a bit too rarely. So apparently the the ingredients do not occur as often as they might occur in reality. This is still a big question mark, as we don't have the data available to prove that point. But I would say this might point towards these specific conditions that we identified were responsible for this temperature anomaly and their nonlinear feedback. This concept of extreme anomalies of common drivers, which was introduced by Erich Fischer and colleagues in their fantastic paper, which just was published during that event. So a perfect timing, really.
Amazing timing.
And yet, what my working hypothesis at this point would be is that models can produce such temperature anomalies. This is also something we see in weather forecasts, which were quite accurate. So models can create those anomalies, but only if they are provided with the right conditions. And apparently, some of those conditions might not be represented sufficiently well, or some of those trends that we observe might not be represented sufficiently well. And another aspect next to the land-atmosphere interaction, I'm particularly interested in are the atmosphere dynamical features and the very interesting dynamics that we have observed during that event. This interaction between a Rossby wave train that emanated from the Pacific and a stationary wave that was already present around the northern hemisphere, which probably led to that extreme geopotential height anomaly. So very complex interactions. And yeah, we don't know if that was just a kind of bad luck situation, or if these types of coinciding wave trains are another effect of climate change. And as most of us are aware of, there's a huge debate on atmosphere dynamical responses to climate change. There's a lot of very interesting research still that still needs to be done.
And I might add that, Kai has been involved in some of that very interesting research on a topic that I think is probably of interest to some of the people who will be listening. This notion that, especially in the Northern Hemisphere warm season, summer months, that there may be, it looks like there is, at least in the real world, a trend towards more persistent or more amplified essentially waviness of the atmospheric pressure patterns. In other words, involving things like quasi-resonance of waves in the atmosphere and the Northern Hemisphere waveguide, which is essentially means that the position and the configuration and the persistence of these wave patterns is partly dictated by the position and strength of the jet streams in the Northern Hemisphere. And it may be the case that they're especially in summer, that they're changing in ways that favor persistence, these stuck wave patterns. And there is, as Kai alluded to, a lot of debate over this in the scientific community. There is genuine uncertainty regarding whether observed trends are going to continue, whether they're caused by climate change or by sort of random bad luck or some natural cycle, whether there's a link to what's happening in the Arctic with the greatly amplified and accelerated warming in the high latitudes and the loss of sea ice. This is a pretty active area of debate that we probably don't have time to get into in detail, but in this conversation, at least, perhaps in the future. But just briefly, is this something that you think could be relevant in the occurrence, especially of these Northern Hemisphere summertime heat extremes? You've talked a lot about the soil moisture feedback, but might there also be something about the way that the persistence of these atmospheric waves is changing that could further accelerate these sorts of things in ways that climate models might not be capturing?
Yes, certainly. I think one has to be really careful about what to like what to discuss in that context. So the waviness itself is a metric that can be diagnosed by a lot of different methods, and to my knowledge, there's not a consistent trend observable in the records of the past 40 years or so yet concerning the persistence. I feel in summertime in particular, there's growing evidence that this is actually taking place, as the observations and models do agree in the sign of change. So the persistence measured by the eddy kinetic energy, so the weakening of the storm tracks in the mid-latitude summer circulation, is something that has been shown repeatedly with different methods. And it seems as if this trend will continue in future in case emissions continue to rise. And of course, increased persistence would also affect the stationarity of particular weather patterns. If this has influenced that particular event is really hard to answer. And yeah, I would not be too confident about it. But overall, I would say, the increased persistence will make summer weather extremes more severe, and that holds also for extreme precipitation. As if you have a case of a specific weather pattern raining down over a specific region, of course, if that region is the same, you will see just more rain coming down on a particular location, which increases the flood risks.
And we've certainly seen a lot of that in the last few years during Northern Hemisphere summer as well. Since we're running up against the hour, I think I'd like to give Sam the last word as lead author of this excellent paper, which I recommend that everyone read if they are so inclined. Sam, any final thoughts on any of these things, either the philosophy of extreme events and how we know what we know, or any specific things that you found most interesting or surprising in this work? Anything along those lines?
I mean, I think you brought up a good framing, that we, in a big picture, sort of, we only have one historical realization of what the climate can produce. So what we have actually observed in the real world. But sort of what we know from climate modeling is that there's a huge amount of variability and chaos in the atmosphere. And so what we really want to understand is what are the plausible things that can happen in the climate system. And so when you bring up the example of, for example, we haven't seen a sort of tropical cyclone hit Dubai or something like that, but there exists the plausibility for that because there's a lot of warm water there, and if there's just the right conditions, something like that can happen. And that's what shifts the conversation from thinking about sort of black swan events that are completely unpredictable towards thinking about things like these still very destructive gray swan events that are a little bit more plausible. And so something like this Pacific Northwest heat wave, I think, raises the question of how can we better understand what is plausible in the Earth system and be prepared for the risks that sort of modeling can tell us could happen in the future, but maybe we haven't observed yet in the past. And thinking about these extraordinarily extreme events and how they are driven and what mechanisms cause them is really important to consider these potentially plausible risks in the scope of what's really possible in the climate system.
I think that's a great way to put it, and it's very consistent with the way that I think about understanding how the events that we've observed over the past century or so, which is really a blink of the eye in the Earth history context, it sometimes doesn't tell us enough about what we want to know about the kinds of events that really affect society and ecology in ways that we really want to understand if they're going to get worse in a warming climate, which in many cases they already appear to be doing. So with that, I just wanted to thank everybody again for joining me and bearing with me through the technical challenges. I think perhaps I'll have you on again in the future when I've really got it nailed down. But thank you so much again. And I really enjoyed our conversation. I hope you did too.
Thank you for having us.
For this
Yeah,
opportunity. It's a really cool new format. I'm excited to see where your YouTube channel goes. This kind of thing.
Excellent. Thanks again.